Electrons, subatomic particles with a negative electrical charge that decide how atoms bond and carry the electric current through our wires. Or are they? It's true that electrons hold atoms together, but the picture we often associate with them is fundamentally wrong. So if they don't follow simple orbits like this, then what do they? Now, before we get into this, we have to understand a little bit more about electrons. This is wrong. Electrons actually have something called wave-particle duality, meaning they can behave like particles and like waves. We can even assign an electron a mathematical wave function. And with wave functions, we have this handy Schrödinger equation. So if we solve it to find the position of an electron, we find that it's more like this. This is a probability cloud, a fuzzy region of space where an electron will probably be found. At any point in time, it could be anywhere in this cloud, but nowhere outside of it. To describe the quantum location of an electron, we use 4 different values that we can think about somewhat like its address. These include its energy level, subshell, orbital, and spin. For the main energy level, or shell, think back to the Bohr model. Electrons are found in these planetary orbits, each with a number. As the number increases, the distance from the nucleus and the size of the orbit increase. But with our new quantum orbitals, it would look a little more like this. In an energy level n, there would be n number of possible sublevels that the electron could reside in. These include the s, p, d, and f orbitals. Technically, G, H, and I exist too, but there's a catch. The energy and distance from the nucleus increases as you go down this list. In reality, for subshells G and onwards, the energy required to fill them is so high that no atom has electrons in them in their ground state. Only a highly excited electron, one that's been pumped with energy, might be able to get there. Next, in each subshell, there are a certain number of orbitals. Each orbital can hold 2 electrons. In subshells with more than one orbital, each one will have different shapes. For example, with the p subshell, there are 3 orbitals: px, py, and pz. Each orbital in a subshell is degenerate, meaning they have the same energy, even if they have slightly different shapes. But as you go to subshells with more electrons, the shape becomes more and more complex. But why are these shapes the way they are? Well, they're all different solutions to the Schrödinger equation for the electron, but with more complex solutions, more complex patterns. Lastly, each electron has a spin. It can either have spin up or spin down. A fully filled orbital has one of each, but spin is kind of weird. This is spin, but this isn't quantum spin. Spin up has a value of exactly positive 1/2, and down has a value of negative 1/2. The electron is somehow spinning with angular momentum, but not actually spinning. If you want to see how it looks like, it's more like this. So now you know how to describe the location of an electron. To recap, they're found in these clouds of probability, not planetary orbits. In these clouds, we can imagine 4 values that determine where they are exactly. Its address. These are its shell, subshell, orbital, and spin. No 2 electrons in the same atom have the same of these 4 values. Each of them must be distinct. This is the first step to understanding why atoms bond the way they do, why some elements react and some can't, even why the periodic table is structured the way it is. So next time you see one of these simple models, remember, the real electrons are far more complex and far more fascinating.